17.7, Part 1, Electrochemistry, Stoichiometry, and Electrolytic Cells, or Electrolysis. These are actually 2 lessons, but when I made my notes, I put them together. But really, you could say that this is separate. Probably I'll just do this and have you do, for the first part, Electrochemistry, Stoichiometry, the stoichiometry problems, do number 1, 2, and 3. It's a lot on the worksheet. Actually, you ought to get that worksheet out, because I think I might do a couple of them for you. I might do some of them for you on the paper as examples. And also, these notes now become really just a lot of information. There's so much extra information in my note packet that you don't have to worry about. So I'm just giving you the big stuff you need to know for AP and for me. So here we go. So anyway, if you find the section on electrolysis, it's under electrolysis. If I ever redid these notes, or it's only one lesson, then what I might do is just make it into 2 lessons. Call one the stoichiometry, and then call electrochem stoichiometry, and then one electrolysis. Because the stoichiometry I'm going to show you is true regardless of the cell that they give you. That you might not understand that what I'm saying right now. I'll explain. Well, look under section 17.7. I am going to probably talk about electrolysis in this lesson. There is what's called an electrochemical cell, a galvanic, voltaic. Those are all the same thing. Everything we've done so far, you take 2 metals, or take a solution in a metal, or a gas in a metal, 2 elements, and you make a battery out of it, okay? That is called an electrochemical cell. Everything we've done before today. Now, I'm going to throw in here and show you now what's called an electrolytic cell. And it's a cell that goes backwards of the original cell. What? And we'll explain that in a moment. But I think before I do that, before I touch on that, I want to jump to stoichiometry. So I'm going to say, if I want to call it 7.7a, I'll make up part whatever. 7-7A. I'm going to call it this. Electrochemistry, stoichiometry. I don't want you to think that this stoichiometry is only true for electrolytic, for the new kind of cell. It works on all the cells. Okay. In electrochemistry, stoichiometry, there are a few things you need to know. One of them is you need to know what a Faraday is. I've already told you about that. 1 Faraday is 485. Wait, what was the number? Can I remember it? It's 96,485. They give you this. They used to put 96,500. So on my answer keys, if you see 96,500, that's just because I don't know why AP just changed it to give you more sig figs. 96,485 coulombs per mole of electrons. The Faraday can relate this many coulombs for every 1 mole. I'm going to put a 1 there. That's a conversion ratio right there. In fact, maybe you want to write it that way. 1 mole electrons has a charge of 96,485 coulombs. Okay, that's the Faraday. So that's one thing you need to know. Another thing you need to know, and I've mentioned to you before as well, what is a volt? 1 volt equals 1 joule per coulomb. All right, for that matter, 1 joule for every 1 coulomb. So a volt equals 1 joule per coulomb. Now, why does that matter? Because if we were to say you have 25, or how about 2.5 volts, that means you have 2.5 joules equal to every 1 coulomb. Every time a coulomb of charge goes by, that's 2.5 joules of energy. So 1 volt is 1 joule per coulomb. You need to know that. So if I have 20 volts, I have 20 joules per coulomb. Okay? And the other one you need to know is called current. Now this is one that is on the formula sheet. On the AP formula sheet, there's an equation that says I equals Q over T. What in the world does that mean? Well, I don't like to use that equation very much, because what I do instead is I put in the units and it explains it. I is called current. Think about current like how fast a river is flowing or a stream. How about how fast is the electrical current going along. All right, think about like a little domino effect. I don't think I even mentioned this yet, but in an atom, let's just say a wire. Say you have a copper wire, and all the copper, you have all the copper atoms in the wire. Okay, we'll spread them out here. Now, the copper atoms, let's say you take away 2 electrons from every copper atom, so that becomes copper plus 2. But now, where are those electrons? Well, they share them in the atom. In the wire. Remember, it's like a crystal. So we'll say here's 2 electrons, electron here, electron there, electron there, electron there, electron there, and there. They share them, and that's what bonds them together. It's a metal bond, the C of electron theory. Okay, so this is our idea that electrons can freely move throughout the wire. So I didn't give myself a lot of space. What happens if I were to come and put something really, really negative right there? Like you go to the wall outlet, and supposedly, well, not supposedly, but it's true, but if you put the wire in one side, that would be like where the negative electron charge comes out, and then it goes through a light bulb. Then the other side of the wall outlet is where it goes back in again. So like, let's draw the little wall outlet, kind of goofy looking right there. But say if you plug a wire here, when you look at the plug, that you plug something in the wall, and you notice that there are actually 2 cables there. But they're put together, they're together. But there are 2 cables, okay? And then maybe they go to like a light bulb or something. I don't know. I wouldn't have a light bulb just sitting on the floor, but whatever. But anyway, so the charge goes in one side, through the filament of the bulb, and back the other. That's the cycle of charge, okay? Well, in that wire, what is happening? If something negative touches that electron, what will happen? That electron is going to move, okay? So let's say it jumps to there. Well, if this electron jumps there, what does that electron do? Now it's going to jump. So here's just something I want you to be aware of. When electricity flows through a wire, you get a wire, you get shocked. You put it into the wall, and it shocks you, okay? Well, here's what did not happen. A single electron did not just zip through the wire and touch you. No. It's more like a domino effect. Think about it that way. The negative charge pushed one electron, and for that matter, maybe both electrons, it moved them over one space. Then those electrons, because opposites attract, but when they're the same charge, they would repel. See, that electron next to the other electron is going to cause it to repel, and it's going to jump. Then it's going to make that electron jump. Then that electron will jump. So anyway, what happened is one electron jumps, jump. And so when you're getting the electrical conductivity, what's going on is just like that, like a domino effect coming through it. I just wanted to throw that at you so you'd know. So it's the electron charge is what flows through it. So the current would be like the river. How fast is that domino charge, the domino effect? How fast is it coming at you? That's called the current. We measure the current in amps. Amperes, actually. Amp is a short for that. You've seen that. Q is equal to the charge, and that's going to be Coulomb. Q is the charge, and it's measured in coulombs. And guess what? T is time, and that's measured in seconds. Now, could they on the AP tell you 25,000 coulombs of charge pass through a wire in 25 seconds? Okay? Could they do that and ask you to calculate the current? They could. They haven't done that before, but you just divide charge divided by time will give you current. Or if they gave you current and charge, you could use that to get time. But what I like to do instead is just think about this. An amp or ampere is a coulomb per second. So an amp, again, it has to do with how much current, how fast the current's moving. When you see the amps for a battery or for what they do is they put what's called a resistor, they put on batteries. But if it says that you have 2.0 amps, that means 2 coulombs per second. So what you're doing, you're regulating kind of like how fast the charge can flow through it. All right, so 2.0 coulombs per second. That's what that means. An amp is a coulomb. If I had, 27 amps, then that means that there's 27 coulombs for every 1 second. Every 1 second, 27 coulombs of charge goes through. So just think of it that way. Amp is coulomb over second. Amp is C over S. That's why I like to, 1 amp equals 1 C over S. So, volt, joule per coulomb, amp, coulomb per second, Faraday, coulomb per mole. This lets you link coulombs to moles, joules to coulombs, and coulombs to seconds. Those are going to be the 3 little steps that you can use. And now, because we're doing stoichiometry, we're going to go back and do something we haven't done in a long time, some factor label method. What? Okay, so here we go. So the first thing I'm going to do, maybe, do I need to talk about electrolysis? No, I think I can, well, I guess I will need to talk about this for a second. Okay. Yeah, I guess I better talk about electrolysis. Yeah, I better tell you a little bit about that. So here is what happens in an electrolytic cell. Let's just say that we were to have a battery set up. Actually, I could use an old one from an old worksheet that we did. Maybe I will, just to make it easier. I'm going to go back to this old worksheet that we already did before with zinc and magnesium. And remember, we had this cell, and in this cell, one side we had zinc, and then one side we had magnesium, and then of course we had our zinc ions down here, and we have our magnesium ions down here, and we have our salt bridge there, okay? And the voltage we calculated was 1.61. 1.61 volt. The standard reaction that occurred in that cell is this. Well, I'll show you. On this side, the zinc ions gain 2 electrons to make zinc, metal. And on this side, the magnesium released 2 electrons, and left behind was magnesium plus 2. So that was the reaction that occurred. And when you calculated the overall reaction, zinc plus 2 plus magnesium gives you zinc plus Mg plus 2. And E of the cell is 1.61 volts. So we put together 2 equations to do that. I mean, there's my messy handwriting right there. You can see that I took one cell and the other cell, got them, I had to flip one. You know, we talked about how we do all that. All right. Actually, I could do some math with that right now. Now that I think about it, before I talk about electrolytic, I could do that if I go to the worksheet. But now, oh, and I do have zinc and magnesium. What a very good thing. What a very good thing. I picked a great one. Okay. That was like I wasn't really planning it, but it worked out good. I wasn't paying attention. Look on the worksheet for the homework today that says electrolytic cells, stoichiometry, electrolysis. Okay, look at that. Let me do this right now before I mention electrolysis. Let me mention this. Okay, it says this. Number 1, a standard voltaic cell is constructed using zinc plus 2, and magnesium plus 2 half cells. The reaction taking place that occurs is this. And it even has the same reaction I wrote. Zinc plus 2 plus magnesium gives you zinc plus magnesium plus 2, and E of the cell is 1.61 volts. So the question is, all right, number 1, it says if a standard cell operates until magnesium ion is 1.10 molar, what's the concentration of zinc in the zinc half cell? Okay, then another cell goes to that with magnesium in that half cell. Okay, so I'll do letter A for you. If I'm going to do that problem right now. If a standard cell, so standard means you started at 1 molar. And you started with 1 molar zinc plus 2. Before you connected the wires. And you had 1 molar magnesium plus 2. So it operates, it says, until the magnesium concentration is 1.10. Now think about this for a minute. It makes sense. As time goes by, look at what's happening in the magnesium cell. That's why it's so good to write these down. Even on a question, just write these underneath the cell. As time goes by, the magnesium metal is getting smaller, right? I'll just exaggerate it. And it's turning into magnesium plus 2 ions. So you're getting more and more magnesium plus 2. So it's increasing molarity. Instead of being 1.0, it becomes 1.10. So let's figure that out for a minute. Get my calculator here. All right, and I also need some space. So that means I'm going to probably, even though I wrote all those down, I guess I'm going to need exactly that space right there to work it. So we'll try to remember all three of those things. Well, you got them on your, those three conversions are very important there. Okay. All right. So it says, a standard cell operates until the magnesium is 1.10. What will be the molarity of the zinc in this cell? If that becomes 1.10, what will that be? Okay, so here's what you got to do. You can imagine 1 liter for each one. All right. Now, if they gave you the volumes, that's okay too. You know, you could use those volumes if you wanted to, but it will be true. They started at 1 mole per liter, 1 mole per liter. So if you went from 1 mole per liter and you went to 1.10 mole per liter, all right, that would be before magnesium, magnesium plus 2. Before, and that will be after. At the end of doing this, you subtract those and you get 0.10 molar is the change. Positive. Now, I'll put a positive number. It went up. So we know that the magnesium molarity went up by 0.10 moles per liter. In fact, we can write 0.10 moles of magnesium plus 2 per liter. Maybe I'll even put a positive there. Just knowing that it increased. It increased. Okay? So what happened to the zinc? So what you need to do is just stoichiometry. So from moles of magnesium, I can go to moles of zinc. And I've got to look at my overall balanced equation. Now, this example I gave you, it's not the best. Well, remember that sometimes you have a number. Like if I had, instead of magnesium, if I had silver, Ag, and Ag plus 1, then I'd have to have 2's in there. It could be a 1 to 2 ratio. But I don't. It's all 1, 1, 1, 1. So 1 magnesium for every 1 zinc. That makes it easy. This is a very important step. Don't forget this step. Look at the equation, the balance equation to go from mole to mole. This is the same as any other stoichiometry you've done. And so that means if the change in molarity of magnesium was 0.10 mole per liter, then the zinc will be also 0.10 mole per liter. But it's going to go down, right? 0.10 moles of zinc per liter are going to decrease because you see that you're losing the ions on this side. So one side, it increases, the other side would decrease. So, for that matter, if you have 1 mole of zinc plus 2 before, and then minus 0.10, I should say mole per liter, change, then after you'd have 0.90 molar zinc plus 2. So you just subtract them, 0.90 molar. That's a pretty easy thing to do, right? Okay. Now on B, you can do that one on your own. And then it talked about did the anode gain or lose mass, and then the question, look at B part. Oh, you know what? I can't really do that one because I want you to do that problem on your own. But I'll do one of them for you. How about this? Okay, I'll just do the same. I'll tell you what. Change number, well, I don't want to mix you up because you'll see the answer key later. But I'll just tell you what. You don't have to do, if you're watching this, for the homework, I want you to do B, number 1 and number 2. Okay? But you don't have to do B, number 3. I'll do number 3 for this other problem. But if you want to just down below the very bottom of the page, let's just do this. Instead of number 3, I'm going to write a new problem. Let me write the question, then it'll make more sense. Okay, so we already know the change right there was 0.10 molar magnesium mole per liter. So for number 3, did the cathode gain or lose mass? Did the cathode gain or lose mass? Calculate the change in mass. Okay. All right, so here's what we'll do. Actually, the same question. I didn't have to do anything. But I'm going to do my problem on the board, not the one on the work. So you'll just skip number 3. When you get to number 3 on the homework, you can just skip it if you want to. You're going to see the answer that I did it for the homework later too, but I'm going to do my own here. Okay, so did the cathode gain or lose mass? All right, first of all, which is the cathode? Remember, cathode, C is a consonant. So CR, C and R consonants, cathode reduction. So this is the reduction. So this is the cathode. The cathode, when we say the cathode lose mass, it's this, the zinc bar. And that will be the anode, because it's where oxidation occurs. So cathode is the zinc. So did the zinc bar gain mass or did it lose mass? Now, to answer that question, this could even be a multiple choice question on an AP exam or on my test. You don't even have to do any math for that, because look at this. Look at the equation. It tells you the zinc ions gained electrons here, and it forms zinc metal. They form zinc metal. They plate it on the metal. And that's what I'll talk about in a next video we'll do later. Or maybe in this one later. But zinc forms on it. So, in other words, mass increase. The cathode gains mass. I'll just say the zinc cathode gains mass. And then to calculate the math, what I'll do is this. I'm going to start with my molarity, my change. Okay, remember, we kind of already did this, but we'll start again from that. It gained mass. So, 0.10 moles, let me move this out of the way too, just so we don't get that yet. Actually, hold on, you'll see that we might need that too. No, I don't know if we might need it. 0.10 moles of, what was it, magnesium. Now, it's also true for zinc, but I'll just start with the magnesium, because that's what I have on the board here. 0.10 moles of magnesium for every liter. And, you know what? To do this problem, you'll have to know how big the container is. You'd have to know that. So we'll just have to say it's a 1 liter container. Just say you have 1 liter volume, 1 liter cell. You have to know the volume. Though the question didn't say it, you'd have to assume it's 1 liter. Because otherwise, you'd only know how much change is in that 1 liter for every 1 liter of solution. If it was 2 liters, then you'd multiply it. So we're just going to say it's 1 liter. This has to be both 1 liter cells, okay? Or if they gave you a 2 liter volume, you put a 2 right there. So the volume is 1 liter. That's how many moles of magnesium ion are going to form. But then from moles of magnesium ion, all you got to do is go to moles of zinc metal. And the same thing, it's also just a 1-to-1 ratio, but you're going to form 1 mole of zinc for every 1 mole of magnesium ion. And then, to get the grams, just use the molar mass. Zinc, we'll go from mole to grams of zinc. And that's going to be 65.39 on the periodic chart. 65.39 grams for every 1 mole. And you multiply that through, and it'll be 1 times 0.10 times 65.39. 6.54 grams of zinc. Okay, so for every liter, 1 liter of this, changing to 0.10, is going to make 0.10 grams of zinc as well. Now notice, I didn't have to say anything about the zinc plus 2 ion, but it's also a 1-to-1 ratio, because it will be true there. And you don't have to involve that. That's what happened. Zinc ions were lost, and they precipitated as iron, as metal zinc there. Okay, all right. So that answers that other question. Now, now I'm going to have to say something about electrolytic cell to do the next part. So what I'll do, I don't know if I want to make another video yet. I don't want to stop it yet. When I'm missing my little timer. I actually do have a timer here, so I don't get behind on my stuff. No, I'm all right. I'll at least start talking about the electrolytic. This is in your notes. Oh, actually, you know what? I might start just talking about it from this cell right here. From this little picture. I'm going to tell you what is meant by electrolytic. This is a very easy thing to remember, I hope. Watch, watch, watch. Okay. Here's big, real important, really important stuff for AP exam. On the AP exam, Most years, they're giving you the FRQs, and they boom, you're going to see a picture of the cell that looks like this. Something, and you're going to see something like that with the cell. You know, nothing filled in. You have to do that yourself. Okay, this is called a voltaic or a galvanic or even electrochemical cell. This is one in which the reaction that occurs is the one that would be spontaneous. The one where E is 1.61 is a positive value, 1.61. Remember, the positive equation stays just as it is written, and the negative one is the one you're going to have to flip. Oh my, I don't think I have my... Where are my list of the values? Where did I put them? Oh, I found them. Good. They're right here. Okay. This thing, the more positive stays as written, and the other one is flipped. That is a voltaic galvanic electrochemical cell. That's the one they usually ask on the AP. But now here's where the fun begins. Every now and then, like maybe every 3 or 4 years, they decide, we're not going to give you an electrochemical galvanic voltaic cell. We're going to give you something called an electrolytic cell. Now, what is an electrolytic cell? One thing about an electrolytic cell is you don't have to have a salt bridge in it. That's one interesting thing, but that's not the big deal. They might not even say the word electrolytic cell, but here is what you will see. It will have a power supply, like a battery or something. Or it could be just a generator or something plugged into the wall. And on that battery, think about like a car battery. There's a positive and a negative terminal. A positive and a negative. Now, watch what I'm going to do here, and you'll see. Normally, what happens, what is the electron charge flow in the normal cell? Okay, well, this is the normal cell, and it says it goes, electrons are released from the magnesium side, and they go to the zinc side. And on the zinc side, so electrons move in this direction. And of course, we have to have the salt bridge there still for that to happen. So they're going counterclockwise. That's the way, and the charge goes that way, and back through the, back through there, and then back through there again, and it goes on and on and on and on, the cycle. That's the way the electron charge is going from here to there. Okay, so what could you do? Could you force it to go in the other direction and force the opposite reaction to occur? Yes, you can. That is an electrolytic cell. So what you'd have to do is, you'd have to have a power supply that is greater than 1.61. So how about this? We'll just make up something like a 9-volt battery, okay? Or it could be a 12-volt battery like in a car, but a 9-volt battery. Now, as long as this voltage is more than the cell voltage, look at what's going to happen. Now, normally the electrons are sent from magnesium to the zinc side. So what I'm going to do is, now I'm going to do it differently. I'm going to send my electrons, maybe I'll use a purple here, a different color. I'm going to send them into that side. I'm going to connect it to the magnesium. Then the positive one, I'm going to connect, well, I used green again, to the zinc. That's going to be messy, too hard to, well, I'll do something here so you can see a little bit differently. I'll put a little bit of white on that one. Yeah, so it looks more like light green. Okay. So what I'm doing is, instead of the electrons being sent to this side and through, now I'm going to send the negative charge to the magnesium and force it to go the other way. That is called an electrolytic cell. Also, that's what happens when you have a battery, like a phone battery, cell phone, computer, iPad, whatever, and you have to charge it now. When you recharge it, you're actually plugging it in the wall and it's making it go backwards. So what will happen? Well, if I had this exact cell and I hooked a 9-volt battery thing on there, now what's going to happen is the reaction itself will be the opposite occurring. Zinc plus Mg plus 2 gives you zinc plus 2 and magnesium. So everything will be reversed that we just saw. The cathode and anode will now change places because where a reduction occurs is a cathode, where the oxidation occurs is the anode, and now the mass of the magnesium was getting smaller. Now the mass of magnesium will get larger, and that will get smaller. So everything will be exactly opposite of what we said if you have a power supply forcing the non-spontaneous reaction. That's a good way to look at it. So now, if you calculate E for that reaction, it is negative 1.61. Negative. So in other words, that will not occur spontaneously. That will not occur thermodynamically favorably. You have to force that to occur by putting a power supply in it. That is an electrolytic cell. So what I always tell people to do, if you notice on the problem that it's an electrolytic cell, and you're going to see a problem, you're going to get to work one like this on probably the next homework, not this one, but when you know it's an electrolytic cell, when you calculate your values, now the one that is negative is the one that's going to be the one that how would you say that? Normally the one that's more positive stays as written. Well, in an electrolytic cell, it will be the other way around. Or what you could do is just think like I did. This is what it would be in a normal cell, but now I got to flip it around. And when you write these two reactions, they'll be the opposite reactions will be occurring. So see, that will not be occurring anymore, and that will not be occurring. They'll be the reverse reactions occurring. Here will be magnesium plus 2 gaining 2 electrons to get magnesium, and here will be zinc, and it will be going into zinc plus 2, releasing 2 electrons. So that's why it's a good idea to always write the equation of what is happening in that cell below it. Another thing, I mentioned it a moment ago and I put it back. In an electrolytic cell, you don't have to have a salt bridge. Okay, you do not have to have a salt bridge in it. And one of the main reasons they like to do electrolytic, one reason is to electroplate. Like they plate something with metal. Like they want to plate, like the most common thing is cars, you look around them now, used to have these things called bumpers. And a bumper used to be made out of metal, like a fender, but I mean not fender, but a bumper. Like a big piece of iron, polished, and then they would cover it with chromium metal. Okay, they would put this in a solution and electroplate it with chromium. Well, electroplating just means, like when, in this case, when magnesium plus 2 solution forms on magnesium, it forms to solid magnesium. It forms on the magnesium, what do you call it? The magnesium electrode right here. Be the cathode, yeah, because it's going down now from positive 2 to 0. But it forms on magnesium. What if I put a different metal in there? What if I put like a copper metal here, and I still put magnesium solution down here? Well, that magnesium would form on the copper. You could magnesium plate it. Usually what you do is copper plate things, or chromium plate them. But okay, I'm going way off right now. But for now, just know if it's an electrolytic cell, the power supply, you're going to have 2 reactions, but it's going to be opposite of what would be give you a positive E. You're going to flip around the other equation so that you get an overall E value that is negative. All right, now that I've done that, let me see if I've got time to do another. It might be about time to pause it and to go on to show you how we do the copper plating. Because right now, oh wow, right now you're able to do all of number 1. You could almost do, no, you can't quite do number 2 yet. I've got to tell you how to do that one problem, and then you can't do the worksheet. You have to hear one more part too, and they're in the notes. I'll do the problems in the notes, but I'll have to take a break because I know I'm not going to have. Probably need about at least 15 more minutes for this lesson. All right, and that'll be all. This one worksheet is all for today, so you can do half the worksheet right now, but then I'm going to have to tell you how to do number 2 right now in the next part. All right.